Hello everyone and welcome back. So this is the very first lesson of this lecture series on Introduction to Graph Theory or IGT. Now before I enter into the very topic of graphs, let me just give you a very brief idea about this course. Now as far as graph theory is concerned, it's quite an interesting topic to study, no doubt. However, we should be well aware about what the course is going to be dealing with. So graph theory basically deals with quite a lot of definitions and terminologies. So in short, it's more of a theoretical subject, or we can say a conceptual one. And if we talk about the applications of graph theory, let me tell you, in our daily life, that is in practical world, we actually use graph theory a lot. Suppose in Google Maps, in rescheduling problems, or as for example to find the shortest distance between two different locations. Apart from all these, in medical field also, as in ECG etc., graph theory is widely implemented. So graphical approach is highly used in our daily routine, knowingly or unknowingly. So we are dealing with it daily. So having said that, let's start today's lesson and enter into the world of graphs. Well, the topics that we are going to cover today in this lesson would be the story behind the origin of graph theory, of course, and after that we will be dealing with some very basic definitions that are required absolutely to understand the concept of graphs. Now, the very first problem that actually gave birth to the idea of graph theory was the Konigsberg bridge problem. So let's know in details what the problem was all about. Well, Konigsberg is a city that is located on the Pregel river in Prussia. So basically, as the river Pregel flows through the city, it divides the city of Konigsberg into 4 different land areas, out of which 2 are islands and the other 2 are the 2 banks of the river. So in this figure, as we can see in this slide, this gives a very rough picture about the city of Konigsberg, how it looks like. So we can see the blue region, as it indicates the Pregel river. It flows through the city and it divides the entire city into 4 land areas. First of all, suppose we have this land area A, which is one of the banks of the Pregel river. We have another bank which is denoted by suppose B. Apart from that, there are 2 islands that are created by the river. One of them is represented by C and the other one is D. So these are the basically 4 land areas that are formed. Now, since there are islands in this city, so there has to be some communication between all the land areas. Now, keeping that in mind, some bridges have been constructed in this city connecting all the land areas. For example, as we can see here, the red lines represent the bridges that have been constructed by the citizens of Konigsberg in order to create a communication among the different lands. So, there are 7 bridges in total as per the requirement. Now, let's see what was the actual Konigsberg bridge problem. Now, to understand the problem, let us simplify this pictorial representation of this city into a more simplified form so that we can get a better picture of it. So, I am basically simplifying the figure a little bit. Suppose this is our river Pregel, due to which the city is divided into 2 islands. Now, this is one bank of the river, this is the other bank. The 2 islands are represented by C and D. This is the Pregel river that I am indicating. Of course, we do have the bridges. So there are 7 bridges in total. A bridge connecting the 2 islands also. So this is the whole picture of the city of Konigsberg. Now, what was the problem? The problem was basically the citizens of Konigsberg thought, is it possible for someone to start a journey from some point and return back to that point after traversing every bridge exactly once? So there are 2 criteria to be satisfied, that you have to start your journey from a certain point, you have to return back to that point, and you have to travel every bridge but only once. So will it be possible or not? That is what is termed as the Konigsberg bridge problem. So this problem was then solved in the 18th century by a Swiss mathematician Leonhard Euler, particularly or precisely in the year 1736. Now, in order to solve this problem, what Euler did was he even further simplified the picture of the city of Konigsberg. Euler indicated the 4 land areas that are created in the city by the Pregel river by some dots or some small circular regions like nodes. to represent the land areas. So these are the two banks of the river on the two sides, and here you have the two islands that are created. So these 4 points actually denote the land areas, and these land areas are connected by some bridges. So he used some straight or curved lines to indicate those bridges between the land areas. For example, between A and C, if you find in the picture, you will be seeing there are 2 bridges. Between the 2 islands, there is a single bridge. Again, between one island and the bank of the river, there are 2 bridges, and from this bank to the other island, there is 1 bridge, and here also you have 1 bridge. So this is a more simplified version of the picture of city of Konigsberg that Euler created. Now this is what is actually termed as a graph. So this gave birth to the idea of graphs by Euler. Okay. So now what was the solution to the problem? Whether it was possible to have a journey with those criteria being satisfied or not, whatever justification was there, we are not going to discuss those details right now. We will be discussing the solution to this problem later on in some successive lecture. Reason being, at this point, being a beginner in graph theory, we need to first know some very basic concepts, some very basic definitions related to graphs, then only we will be able to understand the solution to this problem. So we have to wait a little bit for that. We will be discussing this problem again in some other lecture. For the time being, just be aware of this problem because this actually originated the graph theoretical concept. So let's move forward. Now, before going into any related definition to graphs, we have to first make it clear what do we mean by a graph actually. So let's see. As we can see in the problem of Konigsberg also, a graph comprises of 2 things. First, the nodes that we have denoted, that Euler has denoted basically, which in graph theoretical approach are called vertices. In singular form, a vertex, and in plural form we call vertices. If you have a single, you have vertex. If you have multiple, you have vertices. And the second component that is important is edge, plural edges. Vertex is basically the nodes that we represent in our graphs. And what is an edge? An edge is a straight line or a curve that joins one vertex to another vertex. As we have seen in the Konigsberg bridge problem, we have edges of this type. We have edges of the curved nature as well. So you see, whenever you draw an edge is not just a line. This is not an edge unless you put the end vertices. Yes, that is the term we use for the vertices that we place at the end of an edge, at the ends of an edge. Okay, these are called the end vertices, or you can also call them end points of an edge. Without these endpoints, you cannot have an edge. Every edge has to start and terminate at an end vertex. So from this idea only, we can say that we cannot have a graph without a vertex. That is the most important part that a graph should have. When you draw a graph, it's mandatory that you have at least one vertex in your graph. You can have more than one vertices also, but at least one vertex should be there. But presence of edge is not mandatory. You can have a graph like I have drawn this one, where there are only vertices, or there is only a single vertex but there is no edge. But you cannot have a graph having an edge but not having vertex, because the moment you think of drawing an edge, you have to put end vertices. That is the reason when we define a graph, we mention that the vertex set of the graph is a non-empty set, because the graph has to contain at least one vertex. But the edge set, there we do not need to mention the term non-empty, because it may or may not have edge in your graph. Now another important point that we need to mention in the definition of graph is about the edge. As I already said, an edge always has to begin and always has to terminate at a vertex. Now can we have an edge with only one end vertex? Because this is an edge where we have two end vertices. This is an edge where we have two end vertices. Okay, any edge we are drawing, we are having two end vertices. Is it possible to have an edge with only a single end vertex? See, if you are to have an edge with a single end vertex, then it is important that the edge originates from a vertex. That has to be done. Now, if it has to have only that vertex as its end vertices, then that edge must be returning back to that vertex only. Then only it is possible कि an edge has only one end vertex. Well, you may think it this way, like this is also an edge whose initial vertex and whose terminal vertex coincide. This edge also has two end vertices, but they merge together. That is the reason you can only visualize a single end vertex. So this is the only case when you have an edge with only one end vertex. Otherwise, every other edge has two end vertices. So never make a mistake like this, drawing an edge without end vertices or drawing only one end vertex and not the other. You always have to switch the ends of an edge by vertices. And in case if the edge starts and return back to the same point, then you can have a single vertex at that point. That is a particular case. So this is the reason we mention another key point in the definition of a graph, that while we mention about edge, we say the endpoints of the edge need not be distinct. For example, here the endpoints are distinct. This is one endpoint, this is another endpoint. But they need not be distinct, because you can have a single endpoint as in here to represent an edge also. Fine. Next is labeling. So whenever you draw a graph G, this is my graph, suppose. So I have 3 vertices in this graph and I have 4 edges in this graph. So how can we label the vertices? To label the vertices, we can use any alphabets. We have the liberty to use any alphabets in small letters preferably. But in standard form, what we do, since vertex starts with V, so we denote the vertices by the small letter V, and we use subscripts. V1 for the first vertex, V2, then V3. The order doesn't matter, in any way you can name it. Okay. So I have 3 vertices, I just name them V1, V2, V3. That is the easiest way. Otherwise, we can use other alphabets also, U, V, W, A, B, C, whatever we want. And what about the edges? For the edges, since it starts with E, so we are habituated generally to represent them by small e and subscripts. This is one edge. This is that particular edge E1 which starts and terminates at the same vertex. Other than that, we have E2 which has 2 distinct endpoints. E3, it also has 2 distinct endpoints. E4, this edge also has 2 distinct endpoints. Only E1 has the single endpoint, that is 2 endpoints being merged together. So this is how basically we label the vertices and edges in a graph. So now if we try to define as a whole what a graph is, we can say a graph is basically an ordered pair. Why ordered pair? Because it needs 2 components. First one is the vertex set, second one is the edge set. We denote them by capital V and capital E, or in a more standard form we write capital VG, capital EG. G indicating the name of the graph within the brackets. Now what is VG? VG is the vertex set of the graph that will give you the entire set of all the vertices in the graph, and EG is the edge set of the graph which will tell you what are the edges present in the graph. As we know what a set is basically something that we write within the braces, curly braces. Okay. Now what is the vertex set for this particular graph G? If this is my graph G, then what would be the VG or the vertex set? It is the set of all the vertices the graph contains. Here the graph contains V1, V2 and V3 as its vertices. So I will put V1, V2 and V3 in the vertex set. Similarly, if you see the edge set, in this graph you have E1, E2, E3 and E4 as the edges. So the edge set will contain all of them. That's it. This is how a graph is composed. So now let's see the definition of a graph properly. So a graph basically is defined as an ordered pair VE or VGEG consisting of non-empty. That is the key term that I have used, because a graph has to contain at least one vertex. So non-empty vertex set VG. Whereas for the edge set we have not used any such term as non-empty, because it is possible to draw a graph without an edge, but it is not possible to have a graph without a vertex. Okay, that's the reason this key point is mentioned as non-empty for only vertex set. where each edge is associated with two vertices. As we have seen, every edge to be associated with two vertices, not necessarily distinct. This is the case when you have an edge starting and terminating at the same vertex. That is why this point has to be mentioned in the definition. Now these two vertices are called its endpoints. You can also call these endpoints as end vertices as mentioned earlier. So this is how we define a graph as a whole. And for an example, we draw a graph and we have shown here for this graph G, the vertex set capital VG is the set containing V1, V2 and V3, and EG, the edge set, is containing the two edges E1 and E2. So this is how we represent a graph. So in this context, I should give you a suggestion that whenever you deal with any term or any definition in graph theory, as I have already mentioned, you are going to deal with a lot of them. So make it a habit to give a suitable example to each definition. Whenever you define any term, put an example for that, so that it would be more clear by your figure that you have understood the concept. Even if your writing is not that appropriate, but giving an example to every definition makes your idea much stronger. Well, let us see another example of a graph. Suppose I have three vertices and I don't have any edge. So what would be the vertex set and what would be the edge set? Now since this graph has three vertices, let me label them as V1, V2, V3. So the vertex set would be the set containing these two vertices. The graph does not contain any edge. So the edge set does not contain anything. It is the empty set and we denote it by phi. Suppose we have a graph like this. Okay, so what will be the vertex set of this graph? Set of all the vertices, let's name them V1, V2, V3, V4. So this becomes your vertex set. Next, the edges. So start labeling them E1, E2, E3, E4, E5, E6, E7, E8, E9. As many straight lines or curves as you can see in your graph, they are all your edges. So our EG would be the set containing E1, E2, E3, E4, E5, E6, E7, E8 and E9. Okay, so now let's move to the next topic. So how can you represent an edge? By the names of the end vertices. So whenever you see an edge, suppose E, as there is only a single edge in this graph G, so I am naming it E without any subscript. There are two vertices, so I name them V1, V2. Okay. So how can we represent our edge E? By the names of the end vertices, we can represent our edge E as V1, V2, or we can also represent it as V2, V1. In the bullet point, we have mentioned UV. So let's name them UV only, suppose UV. As I have told, you can label your vertices in any alphabets you want. Then E can be represented as UV or can also be represented as VU. Order doesn't matter. So who is initial vertex, who is terminal vertex, that is not important to me. Just name your edge and you can represent that edge in terms of the end vertices in any order you want. That is why an edge is unordered pair. Order doesn't matter. Next, adjacency or being neighbors. This is very important concept in graph theory. Make it very much clear. What do we mean by adjacent vertices? Let's draw a graph G. Suppose it has 5 vertices. Let's name them U, V, W, X, Y. I am not labeling the edges currently as I am dealing with vertices right now. So what do we mean by adjacent vertices or neighbors? Let's deal with the vertex U. So who are the neighbors of U or who are the vertices which are adjacent to U? Same thing. So U will be adjacent to those vertices or U will be called neighbor to those particular vertices with whom you will find a direct edge from U to that vertex. For example, here we can see U and W are joined together by a direct edge. So, U and W will be called neighbors or adjacent vertices. Similarly, U and V are also having a direct edge between them. So, we can say U and V are also neighbors. If you see U and X, then you don't find any direct edge between U and X. So, you have to search for direct edge. A direct edge should be there. Since this edge is not there, that is why we say U and X, these two vertices are non-neighbors or non-adjacent. Again, if you see U and Y, you will not find any direct edge from U to Y. Okay, what we are searching for is direct edge. We are not searching for any path leading us to that point. Correct? So, you have to search. If you have a direct edge from one vertex to another vertex, then only they will be called neighbors or adjacent vertices, otherwise not. So, in that sense, U is adjacent to W, and how we denote it? We denote it like this. U is adjacent to W, or U and W are neighbors. Same notation we use for both the terms. U is adjacent to V, or U and V are neighbors to each other. Then we can see V is adjacent to X, because between V and X there is direct edge. X is adjacent to Y. Again, V is adjacent to Y. So, whenever you see a direct edge between two vertices, those two vertices will be called adjacent vertices or neighbors. Next, incidence. We say that a vertex is incident on an edge, or we say the edge is incident upon that vertex only when we see that vertex as an endpoint of that particular edge. So, if you have an edge in a graph with the two endpoints as U and V, suppose, then we can say V is incident on the edge E, or U is incident on the edge E. We can also say it like this: the edge E is incident upon the two vertices U and V. So, that is a relation which exists between an edge and its end vertices, where we use the term incidence. Incidence, this particular term can also be used for edges. Two edges can also be called incident upon each other. How? Suppose this is my graph G. Edges are E1, E2, E3, E4. Vertices are V1, V2, V3 and V4. So, here we can see the edges E1 and E2 share one of their endpoints. E1 is the edge V1, V2. See, I am writing the edge in terms of its endpoints. The edge E2 is V2, V3. So, we can see these two edges share one endpoint. V2 endpoint is common to both the edges. We can call those edges incident edges. Okay, or we can also call them adjacent edges sometimes. So, instead of incident, we can also use the word adjacent edges. Next, we move to some very important topics in graph theory called loops and multiple edges. Let's discuss about these. Now, what is loop? Loop has already been discussed earlier in this lecture, only the name I have not stated earlier. So, basically an edge which starts and terminates at the same end vertex, that is an edge whose both the endpoints are same, they are coincident or they merge together. That edge is called a loop. So, a loop is nothing but it is defined as an edge only whose both the endpoints are same. And when you define a loop, you give an example for a loop, that's it. So, in a graph, suppose this is my graph G. So, this is my graph G having three vertices V1, V2, V3, and how many edges? You count the straight lines, the curved lines, the loops, whatever are there, they will all represent edges. So, you have E1, E2, E3, E4, E5 and E6. There are 6 edges in the graph in total. Another important thing, on one particular vertex you can have multiple loops. So, here in this graph there are 3 loops in total. Which are they? E4, E5 and E6. So, let us see the definition. A loop is an edge whose endpoints are equal or same, and we give an example for that. This is a loop, E2 is a loop in the graph G. Next, we move to the concept of multiple edges. It's very important that you mention multiple edges. It's never multiple edge. This is because whenever you talk about multiple edges, you are basically talking about more than one edge. That is the reason it's always edges. Another name that we give is parallel edges. You can also call them parallel edges or multiple edges. Now what are they? This also we have already drawn in many graphs earlier, just we need to know the term. So in a graph G, let me draw one. So here I have three vertices V1, V2, V3 and I have three edges E1, E2 and E3. So who are multiple edges in this graph? Those edges in a graph who share both their endpoints, they are called multiple edges. So if you represent your edges in terms of the end vertices, you will see E1 is V1, V2 because E1 is having V1 and V2 as its end vertices. For E2, we have V1, V3. For E3, we have V1, V3. So when you represent the edges in terms of the end vertices, you will find in this graph E2 and E3 are having the same vertices as their endpoints. So V1 and V3 are not only the endpoints of the edge E2, but they are also the endpoints of the edge E3. So E2 and E3, they are multiple edges or parallel edges. So that's the definition. When you see two or more edges in a graph sharing both their endpoints among them, they will be called multiple or parallel edges. It's not mandatory that you will be having only a pair of edges, you can have many multiple edges. On the same pair of vertices, you can have many number of multiple or parallel edges. So let's see the definition. Multiple or parallel edges are the edges having the same pair of endpoints. As in this particular graph G in the figure, we can see E3 and E4 are the multiple edges. Now let's check loops and multiple edges both together in a graph. Suppose G is a graph. Okay, so in this graph, we have the vertices V1, V2, V3, V4. Edges are E1, E2, E3, E4, E5, E6, E7, E8 and E9. So whatever we have studied, let's just revise once. The vertex set of the graph VG is the set containing V1, V2, V3 and V4. The edge set of the graph is the set containing all the edges E1, E2, dot dot dot. I am not writing the edges, there are 9, you should write all of them. So we have 4 vertices and 9 edges. How many loops are there? As we can see, the edges E1, E8 and E9, they are the loops in the graph. And what about multiple edges? As we can see here, let me write it here, E2, E3, E4. These are multiple edges. Again we have another set of multiple edges E5 and E6. They are also multiple edges. If there are loops or multiple edges in a graph, they will be very clearly visible. For loops, you will be seeing some edges which are standing on the single vertex, they will be loops. And for multiple edges, you will find a pair of vertices on which there are multiple number of edges incident upon. So that's how we distinguish between loops and multiple edges, and do remember these are edges only. So when you count the number of edges in your graph, you count loops also, you count the multiple edges individually. Next we move to the classification of graphs based on the presence and absence of these loops and multiple edges. The first one is the very important one, simple graph. We will be dealing with this graph like all the time, maybe in every lecture. So simple graph is a graph which is simple. Simple in what sense? There are no complications of loops and multiple edges. So a graph which does not contain loops and does not contain multiple edges, that graph will be called simple. For example, I can draw any graph where I don't draw any loop and I don't draw any multiple edge. I can draw this. See, this is a graph in which you don't have any loops, very clear. You don't have any multiple edges. You have the vertices V1, V2, V3, V4, V5. Here we have only one edge between the vertices V2, V5, only one edge between the vertices V2, V4, same for V4, V5, V4, V3, V2, V3 or V2, V1. So, this graph is free from loops, this graph is free from multiple edges. That is why this graph is simple. So, you should not have loops, no loops and no multiple edges. That makes the graph simple. Next, multigraph. As the name itself suggests, multi. So, the graph has to have multiple edges. So, the first condition is there should not be any loop in the graph, and second condition is the graph should contain multiple edges. Then we call the graph multigraph. For example, let's draw a graph which is free from loops but has multiple edges. Okay, so I have drawn a graph in which we don't have any loop at any vertex and I have a pair of multiple edges E1, E2. E1 and E2 are multiple edges because they share the same pair of end vertices. That makes the graph a multigraph. So, loop should not be there, but the graph should contain multiple edges, then only it will be called multigraph. And the last classification is on this basis the pseudographs. So, what is a pseudograph? A graph which contains both loops and multiple edges, that is called pseudograph. So, it should have loops, at least one loop, and it should have multiple edges. So, let us draw a graph which has loop as well as multiple edges. So, this is an example of a graph where you have multiple edges E1, E2, E3 are multiple edges sharing the same pair of endpoints, and we have E4 as a loop in this graph. So, this is a graph having loop as well as multiple edges. This makes it a pseudograph. So, let us look into the definitions. A simple graph is a graph having no loops and no multiple edges. For example, in this graph in the figure, we don't have any loops, we don't have any multiple edges. So, it is simple. Multigraph is a graph having multiple edges but no loops. So, a graph that should have multiple edges but should not have loop, that makes it multigraph. It is easy to remember by the name itself. Next is pseudograph, a graph having loops as well as multiple edges. So, here is an example where we have a loop also, we have multiple edges as well. The last two definitions of today's lecture, order and size of a graph. So, order of a graph is basically the number of vertices you have in your graph, and the size of a graph is the number of edges we have in the graph. So, count the number of vertices, whatever you can see in your graph, that will be the order, and count the number of edges. Now, when you count the number of edges, make sure you are counting every multiple edge individually, you are counting every loop as an edge. So, the total number of edges in the graph will give you the size of the graph. And as far as the notations are concerned, order of any graph G is denoted by small ng, and the size, that is the number of edges, is denoted by small e of G. So, let us see some examples. Suppose I draw a graph. So, here I have drawn a simple graph because there are no loops, there are no multiple edges. So, what is the order of this graph? Ng is equal to the number of vertices you have, 1, 2, 3, 4, 5, 6. Just count them, 6, that is the number of vertices. So, basically for this graph, if we express the vertex set of this graph v1, v2, v3, v4, v5, v6. So capital VG will be the set containing v1, v2 up to v6, the 6 vertices. So NG is nothing but the order of the graph, that is the cardinality of VG, the cardinality of this set of vertices. How many vertices are there in the vertex set? That is the order only 6. Okay, so you count the number of vertices and you write the order of the graph. And what would be the size of the graph? The number of edges that we have in the graph. So we have 1, 2, 3, 4, 5 edges. So the size is 5. Similarly, if we express the edge set of the graph, we have E1, E2, E3, E4 and E5. So edge set contains E1, E2 up to E5, these 5 edges. So size of the graph is nothing but the cardinality of the edge set of the graph. That is how many elements are there in the edge set, that is how many edges are there. Let's see another example. Suppose we have a graph which has only vertices and no edge. So what will be the order of the graph? As many vertices you have? 1, 2, 3, 4, 5, 6 vertices are there, so the order of the graph is 6. And what about the size of the graph? The graph does not contain any edge, so the number of edges is 0. So the size of the graph is 0. Next, let's see a pseudo graph, for example. So the order of the graph NG is the number of vertices we have 1, 2, 3. So order is 3. Size of the graph is the number of edges that we have. Very carefully we should count the number of edges. So we have 1, 2, 3, 4, 5, 6, 7, 8 and 9. So the size of the graph is 9. Let's see some more examples in the figures of the slides. So here in this graph we have order as 4, number of vertices, and the size of the graph, the number of edges. If we count 1, 2, 3, 4, 5, 6, 7 edges are there, so the size is 7. Here we have 3 vertices, so order is 3 and the size is 2 because we have 2 edges. Here we have 2 vertices, so order is 2. There are 2 edges because every loop is an edge, so the size of the graph is also 2. Here we have 3 vertices, so order is 3. We have 4 edges in total, makes the size 4. In this graph we have 4 vertices, so the order is 4 and the size of the graph is the number of edges, that is 1, 2, 3, 4, 5. So the size is 5. Here it's a pseudo graph. We have 3 vertices, so order is 3. We have 1, 2, 3, 4 edges, makes the size 4. Here in this graph we have only 4 vertices and no edge, so makes the order 4 and the size of the graph is 0. Here we have 3 vertices, so the order of the graph is 3 and the number of edges 1, 2, 3, 4, 5. So size is 5. Now in this particular graph, if we count the number of vertices very carefully, we will find there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. So the order of the graph is 10 and the number of edges, counted very carefully, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So there are 15 edges in total, makes the size of the graph 15. Now this particular graph has a name. The name is the Peterson graph. This is a very important graph, the Peterson graph. We are definitely going to deal with this graph in many successive lectures. Whenever we learn a new concept, we can see if that satisfies for the Peterson graph or not particularly. So you can practice drawing this particular graph, Peterson graph. Let me show you how you can draw this graph very easily. So first draw this figure. Draw this figure and please don't mention it as a star, because in graph theory we are going to learn a concept called star graph, and this particular figure does not satisfy the condition of star graph. So make it a habit to not call this a star. So draw this structure, and then from every corner, you draw an edge. The moment you draw an edge, you are bound to put an end vertex at the other end. Okay. So from a corner, draw an edge, put an end vertex. Draw an edge, put an end vertex, because without the end vertices, your edge is not complete. Now after you have drawn edges from every corner of that structure, draw the outline. So these are the edges making those vertices adjacent. So this is what completes your Peterson graph. Now Peterson graph has different structures in the sense the same graph can be redrawn in different orientations. So there are many structures. I find this the easiest one. So eventually when we will be discussing Peterson graph in more details, maybe we will be looking into the other structures as well. So this is the Peterson graph. Keep practicing the graph, how to draw. Lastly, we have a problem for our practice. So let's see what problem is there for us. Okay, so here we are given that there is a set S which contains 6 elements. The elements are 2, 3, 5, 7, 9 and 12. Our question is to construct a simple graph. Okay, so this is one important point that we should remember. The graph has to be simple graph. Now what do you mean by simple? It should have no loop. It should not have any multiple edges. Fine. Such that Vg will be equal to S. So the graph G should be such that the vertex set of the graph is the set S itself. And how to draw the edges? There is a criteria given, basically which pairs of vertices should be made adjacent in the graph. So it's given that AB belongs to EG. Now let's see what AB is. In the very end it's written AB belong to S. So A and B are nothing but the elements of S. Say 5 and 7, 2 and 9, elements of S. So AB will belong to the EG, that is edge set of the graph, that is this AB will be an edge of the graph, that is 2 vertices will be made adjacent if and only if A plus B belongs to S or the modulus of A minus B belongs to S. That means for any 2 elements in the set S, that is in the vertex set of the graph, if the 2 integers make a sum that is also an element of the same set S, or if their positive difference gives me again an element of the set S, then only the 2 elements will be made adjacent. Let me make it more clear. First, our job is to list down all the given information. So we need to draw a simple graph. Very important. Graph has to be simple. Next, name of the graph is G. The vertex set of the graph is the set S itself. So the Vg is going to be 2, 3, 5, 7, 9, 12. So at the very moment we understood that there are going to be 6 vertices in your graph, and the labelings for those vertices would be 2, 3, 5, 7, 9 and 12. So these will be the labelings that we will be using for the vertices in our graph. Next is the edge set. Now it's given the edge set will contain the elements AB, that is AB will be an edge, A and B are elements of S. For example, let me tell you, suppose we take the pair 2, 3. So A is your 2, B is your 3. Now AB, that is 2, 3, this edge will belong to capital EG. Belonging to capital EG means that is an edge. So 2, 3 will be an edge, that is 2 and 3 will be adjacent when you will find A plus B belongs to S, that is 2 plus 3, either this will belong to S, that is 5, or the positive difference of 2 and 3, that is 1. When you take the modulus, minus 1 becomes 1, that belongs to S. So we can see the positive difference of 2 and 3 is 1, that does not belong to S, but the sum of 2 and 3 is 5 and that belongs to S. So when either of the 2 conditions is satisfied, we can say the 2 corresponding vertices A and B are adjacent in the graph. So we can see for 2 and 3, for this particular pair, their sum is an element of our set only. That means the vertices 2 and 3 will be made adjacent. So let's draw the graph. Since Vg is going to be the set 2, 3, 5, 7, 9, 12. So let's draw the vertices 2, 3, 5, 7, 9, 12. Now when we are given the order of the graph, it's better to place the vertices in a circular fashion. Now after our vertices are placed properly, now our idea is to construct the graph by drawing the edges. So we should know where to draw the edges, which particular pairs of vertices should be made adjacent or should be made neighbors. So for that, there is an information given in the question that if we find two vertices A and B such that either their sum belongs to the vertex set or their positive difference belongs to the vertex set, even if both are satisfied, then we are supposed to draw an edge between those two vertices. So our job is to check for every pair of vertices that we can have in this vertex set. So let's start with the very first pair, suppose 2 and 3. Now 2 plus 3 gives us 5, which is an element of the vertex set. That satisfies the given criteria. So we need not check the other criteria for the positive difference. If not satisfied, then we have to check the other criteria also. So here it is satisfied, so we draw an edge between 2, 3. The next pair that we are going to choose is 2, 5. So fix one vertex. I have fixed 2 first. So with 2, whatever pair of vertices I can have, I will check for every such pair. Then I move my focus to the next vertex 3. That is how we do. So after 2, 3, I will move to the pair 2, 5. Now 2 plus 5, this sum is 7, which is again an element of my vertex set, enough for me to know that there is an edge between 2 and 5. Then the next pair is 2 and 7, their sum is 9, which also belongs to the vertex set. So we have an edge between 2 and 7. Next is 2, 9. So 2 plus 9 gives me 11. Now 11 is not an element of the vertex set of the graph. Since this is not satisfied, don't think that there will not be any edge between 2 and 9, because we have another criteria that can be satisfied. So let's check the other criteria. 2 minus 9, the positive difference. So 2 minus 9 is minus 7, whose modulus is 7. Now 7 belongs to the vertex set. See, even if the first condition is not satisfied, I went to check the second condition, which gets satisfied. So there should be an edge between 2 and 9. Okay. In the earlier cases, I didn't check the second condition because the first condition was already satisfied. Okay, that's the reason. So next, between 2 and 12, their sum is 14, that does not belong to the vertex set. So we move to check the next condition. 2 minus 12 modulus, that is 10, it also does not belong to VG. Now when both the conditions are not satisfied, that means these two vertices will not be made adjacent. So there will be no edge between 2 and 12. So we are done with every pair that can be created with the vertex 2. Now we move our focus to the vertex 3. So the very first pair we have with 3 is 3, 5, because 3, 2 is already checked. Now we move to 3, 5. So between 3 and 5, their sum is 8, which is not an element of the vertex set, but their positive difference is 2. So 2 belongs to the set, so we draw an edge. Then with 3 and 7, sum is 10, not an element of VG, positive difference is 4, which is also not an element of VG, so we don't draw any edge between 3, 7. Between 3 and 9, their sum is 12. 12 is an element of VG, so we join 3 and 9. 3 and 12, their sum is 15, not an element of VG, but their positive difference is 9, that is element of VG, so we draw an edge between 3 and 12. Next, we move our focus to 5. So we do the same thing and we check for 5, 7, positive difference is 2, that is an element, so we draw an edge. Between 5 and 9, the sum is 14, the positive difference is 4, both of them are not the elements of VG, so we don't draw any edge between 5 and 9. Between 5 and 12, the sum is not present in the set, but their positive difference is 7 and it is present in VG, so we draw an edge between 5 and 12. Next, we move our focus to 7. So between 7 and 9, we are not checking for the earlier pairs because they are already checked. So between 7 and 9, positive difference is 2, that is an element here, so we draw an edge. Between 7 and 12, their positive difference is 5, which is an element here, so we draw an edge. Between 9 and 12, the sum does not belong to the vertex set, but their positive difference is 3, which belongs, so we draw an edge between them. Up to this, you will find all the pairs have been checked, and this is the graph that we obtain as our graph G. So this is our graph G, and if we count, we have 6 vertices in the graph, that is already given as the cardinality of the set S. So the order of the graph NG is 6, and if you count the number of edges properly, you will find there are 12 edges in the graph. So the size of the graph is 12. And this is a simple graph because we don't have any loops, we don't have any multiple edges. Well, so that's all for today. We are going to meet you again with the next lecture of this series. Till then, thanks for watching, and we wholeheartedly welcome you for any queries and suggestions. So if you do have any, please do comment below. Thank you.